I'm Jeff Yarger. I'm a professor of chemistry, biochemistry, and physics at Arizona State University in the School of Molecular Sciences. I'm here today to introduce calorimetry and some of the primary calorimetric techniques we use in measuring thermodynamics, with an emphasis on biological systems. So calorimetry is really measuring heat. And so most of the time, and calorimetry is the primary technique, experimental technique we use in getting a grasp experimentally on thermodynamics of chemical or biochemical systems. It's really at the heart of what we use experimentally to get at thermodynamic parameters. And we can do this in an indirect way. A long time ago, or even now, it's sometimes common to look at things like, for example, someone's metabolic, how much oxygen and CO2 they're using, and then infer based on the chemistry behind it, what thermodynamics is going on. But really what we're going to focus on, and what is focused on in the chemical and biological sciences, is direct calorimetry, or direct measure of heat or heat transfer in some shape or form. And so there's lots of different types of calorimetry, and I'm going to focus on the ones that are the most popular and most used in the biological sciences, health, medical field, chemical sciences, etc., and to measure heat. And I'm broken this up into kind of four primary ones. The first one you often see in introductory classes, which is an isobaric calorimeter, constant pressure, or an isochoric calorimeter, constant volume, which is often called a bomb calorimeter. And then I want to get to two techniques that are very common in research and advanced calorimetry that are used a lot in the biological sciences for phase transitions, and what I would call modern calorimetry you would see in pharmaceutical industries and medical industries, food industries today, which are isothermal titration calorimetry, we often just say ITC, and differential scanning calorimetry, which we often just say is DSC. So isobaric calorimetry, often called by several different names. In introductory chemistry classes or physics classes, they'll often even be called coffee cup calorimeters or styrofoam cup calorimeters, because these are often the apparatuses used, to, in a sense, crudely, try to create an adiabatic container, something where heat cannot transfer out, and they do that by styrofoam cups or thermal insulators, dewars or styrofoam cups or coffee cups, etc. A lid, something over the top to keep evaporation from happening, etc. At the heart of the calorimeter, and then it's often stirred so that just anything mixes quickly, or that everything remains isotropic at all times. But the heart of it is really just measuring temperature. And so, and this is commonly done for, two common things would be, for example, if you want to know the heat in some reaction, like if you have an acid like HCl and a base like sodium hydroxide, and you mix them and you want to know, is that endothermic or exothermic? Is heat evolved or is heat absorbed in the system, etc.? You can do that in this and watch the change in temperature. And since you're doing it under constant pressure conditions, it's not, the energy term you're looking at is the enthalpy, so that we're looking under constant pressure conditions, and we have our closed system where we put everything into it. So there's no change, after the reaction in a number of moles, or you're putting something in and then it's a closed system after that. And so really, the enthalpy is just, the change in enthalpy is related to the change in heat. And we usually assume that these are things that over the temperature range we're looking at, that heat capacity is constant, et cetera. So really we're just looking, the enthalpy is just directly proportional to the heat capacity and then the change in temperature, which we experimentally measure. And so we use this oftentimes to, for example, if we have the heat capacity, we put water in there and we want to know the heat capacity of an unknown material, we can put it in there at a different temperature, let it equilibrate, get the change in temperature, and then determine what the heat capacity of something is. Or we can get the enthalpy of some process, some reaction, et cetera. And so this is commonly what's done with this type of calorimeter. And usually the sophistication just comes in how you make this more adiabatic, or where heat doesn't transfer to the surroundings. And you're really, all the heat is contained within the system. Then moving on, instead of at constant pressure, you can work under constant volume. And in this case, under constant volume, so the work term goes away and you typically look at the internal energy directly of the system. And this is typically called bomb calorimetry because you're usually often loading something. And the most common way to do this is to do this with an oxygen bomb, so that you're really looking directly at combustion. This is common in the food industry, pharmaceutical industry, et cetera. And so you'll put a sample into it, you'll load oxygen at high pressure, but the whole thing is under constant volume conditions. And then you do something to ignite it to have that hopefully completely combust. All combustion reactions will be exothermic. They will therefore cause a change in temperature of the surrounding water. You can do it of a known material to get the heat capacity of your whole system. And then after that, once you have the heat capacity of your bomb by having it calibrated or having some known systems done, now anything you put in there, you can in a sense back calculate what the heat of combustion was. And through Hess's law, et cetera, you can therefore get back out, if you know the materials that were put in, et cetera, what the heat of formations were, et cetera. The raw data typically looks something like this. You have your water at a certain temperature. It's equilibrating over time. You ignite the bomb, and you see the temperature of the water rise and eventually level off. And you would like it, of course, to be at a constant temperature, to raise and then stay at a constant temperature. That would be ideal. But of course, experimentally, you have this thing approaching room temperature, so it's changing a little over time, and then eventually, again, approaching room temperature here. So we often have to get at the delta T by extrapolating from where it's equilibrating at. And often we do that not just at the midpoint, but where the area here is equal to the area below is a common way, as I've shown over here. And we often take into account the wires that were used to ignite it. In other words, a lot of the details to make sure we get as thermodynamically accurate as possible in this process. So in biological systems, oftentimes the change in heat, unlike something like combustion or looking at bulk amounts of material where you can use milliliters to pour and see large temperature changes, oftentimes these things are very small changes in energy or, in a sense, associated heat or temperature that would be involved. And a technique that has come up that is used extensively in biological systems, especially for things like looking at how ligands bind to certain molecules, macromolecules in solution. So, for example, how a ligand would bind to a protein or how it would bind to the groove of DNA or something like that, is using isothermal titration calorimetry, or ITC, where in a sense you have often your ligand here and your macromolecule in solution. You have a reference cell that has the buffer or whatever, the solution minus the macromolecule. And you're titrating discrete amounts of material in one at a time and seeing how that, watching that heat effect. So watching that go in and cause a heat effect, et cetera. And then you're using this to keep it isothermal or at the same temperature. And so this is also under constant pressure conditions. So in a sense, when we're looking at these individually, you're getting something about under constant pressure, that the heat involved is related to the enthalpy. But because we're doing this not only under constant temperature, but constant constant pressure, but also constant temperature, in a sense, this is related to the change in free energy or the equilibrium constant. And so fitting this gives you directly something about the Gibbs free energy or the equilibrium constant for this non-covalent metal-ligand interaction, which is very useful in biological systems. So also, probably the most used thermodynamic calorimetry technique is differential scanning calorimetry. And again, typically we're doing this more or less under constant pressure conditions. So what we're looking at as we change the temperature is something related, is the heat, and that heat is related to the enthalpy directly because we're under constant pressure conditions. We're doing this usually in a closed system where we have our sample in one container. Our reference contains everything except the sample. And we're watching the heat flow, trying to, at all times, keep these at the same temperature as they go through. But if your sample goes through an endothermic or exothermic technique, it'll take extra power or heat flux to compensate to keep those at the same temperature, and that's what you're watching. That's directly proportional in a sense to how the heat capacity is changing. So in a sense, this is, giving you a measure of how the heat capacity changes as a function of temperature in your system. And you can either do heating or cooling of this, and you can scan at different rates and see, anything that causes a heat effect or an enthalpy change in your system. So analogous to differential scanning calorimetry is differential thermal analysis. And these are really more or less the same technique, just with different, slightly different instrumentation used in doing it. But it's still typically scanning temperature and doing a difference across, trying to keep your sample and reference at the same temperature. So really, DTA is very similar to DSC. So this overviews some of the primary techniques we use in calorimetry, which will hopefully help you when we look at specific examples of using calorimetric data, both simulated, experimental data given to you, or being able to collect the data yourself to use this in determining thermodynamics of biological and chemical systems. Thank you.